So now we're on to the second half of Chapter 12, and we're going to be working on the inferential statistical theory, and in particular how we get a sense of how close an estimate may be to an actual population value. So a sampling distribution is the key tool that we're going to use to estimate sampling error. Sampling error being, in essence, the difference between the population parameter and the sample statistic. So what is the sampling distribution of a statistic? It is the distribution that results from selecting an infinite number of random samples of the same size from a population, all samples being selected from the same population. A sampling distribution's cases are the statistics from the samples that are drawn, so that, for instance, one could build a sampling distribution that was composed of means. One could build one for percentages or perhaps for frequencies, that is, counts. And the next slide will demonstrate the process step by step. So how specifically does one build a sampling distribution? So select a random sample of given size from a population. Calculate the chosen statistic for this sample. So one might select a random sample and, for instance, calculate the mean of this sample. So you'd calculate the statistic and then you would plot the statistic. And then the fourth step would be to repeat the first three steps an infinite number of times. So you'd choose an infinite number of random samples of the same size. You'd calculate and then plot the statistic of choice, and then you would repeat those steps infinitely. Now, in reality, researchers don't select an infinite number of samples to build a sampling distribution. Rather, researchers use statistical theory to build the distribution. So what we're going to do here is demonstrate a sampling distribution. And our sampling distribution is in essence going to be a count. We are going to build a sampling distribution of the number of heads that are obtained from tossing an unbiased coin 1, 2, and 10 times. So a sampling distribution where n equals 1 is one and the same as a frequency distribution. What distribution would we get if we tossed an unbiased coin once and recorded the number of heads that we obtained in that sample? And we need to repeat that process infinitely according to theory. But an unbiased coin comes up heads 50% of the time, so that in the long run, that is, if we tossed the coin an infinite number of times, we would get 0 heads in 50% of samples, and we would get 1 head in 50% of samples. And I mean, I'm not going to show the statistical formula that leads to that result. I mean, it's an intuitive result here. So I've plotted a percentage of samples in which we would obtain 0 heads and 1 head. And this is indeed our sampling distribution. We're building a distribution here, and that distribution shows the 50-50 split between 0 and 1 head. Now let's go ahead and build a sampling distribution of the number of heads where n equals 2, in other words, where we toss our unbiased coin 2 times and then record the number of heads. Well, statistical theory, and we won't get into that theory, tells us that in the long run we would obtain 0 heads 25% of the time, 1 head 50% of the time, and 2 heads 25% of the time, which is to say in 25% of our random samples. So therefore our sampling distribution would look like this. We would get 1 head 50% of the time, and 0 and 2 heads 25% of the time. Now let's go ahead and increase our sample size to 10. We're going to toss our unbiased coin 10 times, and we're going to count the number of heads in each of those samples of size 10. And again, we don't in reality have to carry out this sampling process infinitely, because we can use statistical theory, and we're not going to cover that theory. But statistical theory can build the sampling distribution that we would get by tossing an unbiased coin 10 times and counting the number of heads. And you can see that the most common result would be 5 heads, and we would obtain 5 heads in almost 25% of our random samples. I mean, the least common results would be 0 head and 1 head, and we would obtain such results, I guess, in just about 1 in every 1,000 random samples that we would carry out. So, in sum, then, a sampling distribution is a distribution of some statistic. I mean, in essence, it's a plot of the distribution of some statistic. And it is the distribution that would emerge if the sampling process was repeated infinitely, and the sample statistic was plotted for that infinite number of samples. Now, a particularly important sampling distribution in statistics is the sampling distribution of the mean, that is, of x bar being the symbol for the mean. And this distribution is the frequency distribution composed of means of an infinite number of random samples of the same size, all selected from the same population. And so to give more detail, to build a sampling distribution of the mean, what you would do would be to select a random sample of given size from some population, calculate the mean of that sample, plot that mean, and step 4, you would repeat the first 3 steps infinitely. In real-world research, these steps are not repeated infinitely, but rather statistical theory is used to build the sampling distribution of the mean. The key theory that underlies the sampling distribution of the mean, in other words, that determines its characteristics and shape and so on, is found in the central limit theorem. The central limit theorem states 3 key points about the sampling distribution of the mean. The first point is that the mean of the sampling distribution of the mean, in other words, the sampling distribution of the mean is the plot of the means from the infinite number of random samples. Well, the mean of that distribution will equal the mean in the population from which samples were randomly selected. So there's the mean of our sampling distribution. Point 2 states that the standard deviation of the sampling distribution that we build will be equal to the standard deviation in the population divided by the square root of the sample size. As you know, shape of distribution is an important characteristic of distributions. And the third point of the central limit theorem states that as sample size increases, the shape of the sampling distribution approaches normality, which is to say, approaches the shape of a normal distribution. Now, This third point is particularly important. It says that the shape of the sampling distribution approaches normality regardless of the shape of the distribution in the population. So suppose that the population distribution is skewed. Even so, as sample size increases, the shape of the sampling distribution of the mean will become closer and closer to normal. And I'm going to add a pragmatic point on to the central limit theorem and state that for almost all distributions that one would encounter in social science research, that is for normal distributions, for skewed distributions, for very peaked distributions, for flat distributions, for bimodal distributions, for rectangular distributions, for other distributional shapes as well. In other words, essentially regardless of the shape of the distribution from which the many random samples are being selected. Regardless of that shape, the shape of the sampling distribution of the mean will be close to normal whenever sample size is 100 or greater. I'm just going to add a technical caveat. I mean, it is possible, for instance, for a distribution to be so very skewed that this point would not hold. So if you had a distribution that was even more strongly skewed than the extreme skew figures in Chapter 5, it's conceivable that sample size might be a little bit larger than 100. But this provides a good pragmatic way for us to move forward. So for our purposes, whenever sample size is 100 or greater, the shape of the sampling distribution is going to be close to normal, regardless of the shape of the distribution in the population from which the samples are selected. So, I mean, our inferential statistics is more abstract than descriptive. So, I mean, we're getting a little abstract, but hopefully we can bring it down to earth. So, there is a term you should know, and that term is the standard error of the mean. And the standard error of the mean is the standard deviation of the sampling distribution of the mean. So here is our formula for the standard error of the mean. So in other words, to determine the standard deviation of the sampling distribution of x bar, what we need to do is we need to take the standard deviation in the population, symbolized by sigma, and we divide by the square root of the sample size. Let's continue to work with our child abuse and neglect reports registry example. And let's presume that in the full population of child abuse and neglect reports, I mean, perhaps there are several 100,000 reports in this population, but in that full population, let's presume that mu, the population mean, is 9, and that sigma, that is the population standard deviation, is 5. And further, let's presume that the shape of the distribution of children's ages is close to uniform, which is to say flat or rectangular. So there are characteristics of our population. Let's use these characteristics in conjunction with the central limit theorem and build a sampling distribution of them. So now here's a glimpse at our population distribution. So we're going to select our many different random samples from this distribution. Now observe that the shape of this distribution is close to uniform, which is to say I mean, there is no bell-shaped curve here. I'm drawing a bell-shaped curve. But rather, the number of kids in different age groups is reasonably the same. I mean, there's a slight upward trend as kids get older. But basically, this is a distribution that is close to flat in its shape. Before we go further, I mean, it's important to keep distributions distinct in your mind. In particular, I mean, recognize that this distribution is not the sampling distribution. We're going to build the sampling distribution by selecting an infinite number of cases of given sample size and plotting the mean. So this is the population distribution, the distribution from which we are going to be selecting our infinite number of random samples. I mean, in reality, we're going to be using statistical theory. Now, and let me make one further point. I mean, the shape of this distribution connects to the third point of the central limit theorem, which is the shape of the sampling distribution will approach normality as sample size increases. So, I mean, this is not a normal distribution, but that's not going to affect our building of the sampling distribution because, as the next slide will show, sample size is going to be 100, and therefore our sampling distribution is going to have a shape very close to normal, even though the population distribution has a very different shape. So what we are going to do is we are going to select an infinite number of random samples of size 100 from the population of child abuse and neglect reports, and we're going to plot the mean of each of these samples. In other words, we are going to build a sampling distribution. And we want to be able to describe this sampling distribution. In particular, we want to be able to describe its mean, its standard deviation, and its shape. So let's do so. So point 1 of the central limit theorem tells us that the mean of the sampling distribution will equal the mean in the population. The population mean is 9, so therefore the mean of our sampling distribution will be 9. Point 2 tells us that the standard deviation of the sampling distribution, that is, the standard error of the mean, will equal the standard deviation in the population divided by the square root of the sample size. We're taking samples of size 100. So we carry out that math, and the standard deviation of our sampling distribution will be 0.5 years. And finally, point 3 of the central limit theorem, in conjunction with the point that I made about sample size being 100 or greater, tells us that the shape of the sampling distribution will be close to normal. Again, it will have this shape close to normal, even though the population distribution has a non-normal shape. Here is our sampling distribution of the mean for children's ages. I mean, we are plotting here the distribution of means that we would get were we to select an infinite number of random samples of size 100. And so the mean of our sampling distribution is 9. The standard deviation of our sampling distribution is 0.5, and the shape of our sampling distribution is close to normal. You'll note I've added a second axis of z-scores, so you can see that the standard deviation of our sampling distribution is indeed 0.5, so that, for instance, 9.5 is one standard deviation above the mean in the sampling distribution. So we come down and we can look at that score as being one standard deviation above the mean, that is, as having a z-score of 1. And for instance, a sample mean of 8 is located 2 standard deviations below the mean. So we could say that the z-score for a sample mean of 8 with respect to the sampling distribution is -2. It is important that the shape of the sampling distribution of the mean is close to normal. Because this is so, we can use the normal distribution to describe it. And now, for instance, it has been burnt into your brain that about 68% of cases in a normal distribution are located within 1 standard deviation of the mean. So in this particular example, the standard deviation is 0.5 years. Therefore, 68% of cases are located between 8.5 and 9.5. In other words, between 9 and plus or minus 1 standard deviation. And here's a visual depiction of where 68% of the cases are located. And similarly, it's the case that in a normal distribution, about 95% of cases are located within 2 standard deviations of the mean, so that therefore in our sampling distribution, about 95% of cases are between 8 and 10. In other words, about 95% are between 9 and plus or minus 2 standard deviations. Now, study of this formula tells us that as sample size, that is to say n, increases, the standard deviation of the sampling distribution will decrease. I mean, that's because the value of the denominator in the formula is getting larger and larger. So let's go ahead and figure out the characteristics of the sampling distribution of the mean for children's ages for some different sample sizes. So when sample size is 100, we've already done our calculations and indeed had a visual display. The mean is 9. The standard deviation, that is to say the standard error of the mean, computed to 0.5 years, and because sample size was indeed 100 or greater, shape is close to normal. Now suppose that we take an infinite number of samples of size 400. The mean of the sampling distribution continues to be 9, but the standard deviation is going to get smaller. The standard deviation is going to become 0.25 years. And the shape is very close to normal. And finally, we could up sample size to 1600, and we could carry out our calculation to see that the standard deviation becomes smaller still. It becomes 0.25 years. So this is demonstrating to us that as sample size increases, the standard deviation of the sampling distribution is decreasing. Here's visual depiction of the sampling distributions in our example for 3 different sample sizes. So you can see the sample means are more spread out here than is the case where sample size is 400, and then that the sampling distribution is narrower still when sample size is 1600. Now, sampling error, in a general sense, is the difference between the population parameter and the sample statistic. You know, for instance, our population parameter, which is to say in our example, the mean in the population is 9. Suppose a given random sample had a mean of 10. Well, then the sampling error would equal 1. Now, on the other hand, if a sample mean was much closer to the population mean, perhaps a sample mean is 8.75, then the sampling error would be minus 0.25. So it's a fundamental characteristic of inferential statistics that as you take larger and larger samples, sampling error tends to decrease, which is to say, as you take larger and larger samples, sample statistics become better and better estimators of population parameters. Now, in actual research, you're going to take only one random sample. And in actual research, you won't know the population mean. So in actual research, you won't know the exact sampling error. But basically, what you can know is that as sample size goes up and up and up, the standard deviation of the sampling distribution, which is to say, it gets narrower. So the sample means and sample statistics in a general sense cluster closer and closer to the population mean, that is, to the population parameter, speaking more generally. So as sample size goes up, the chances are that your sample statistic is closer and closer to the unknown population parameter. So the sampling distribution is really going to be our key to this task of being able to generate good estimates about how close our sample statistic is likely to be to our unknown population parameter. So chapter 13 is going to take us forward to one of the major applications of inferential statistics, and that is confidence intervals.